Hello, everyone. Let's talk about a Newman projection and let's learn how to write a Newman projection. So first off, in your problems in the exam, they will give you a bond line structure, meaning they will give you a structure which will look like this, right? So right now we have a 2-carbon structure and that looks like this. So I'm just going to say pink on top, right? And then let's say this is your wedge because this is coming towards you and this is a green, all right? And then this is a dash. And that is an orange ball. So if you are able to understand what the structure really means, right, then you would know that it means nothing but the orientation of a molecule such that there's one behind you, one in front of you, and one on top, okay? All right, and then the second bond connected to the carbon again, this is a carbon ball, and that's also a carbon ball, right? And then to those carbon balls, there's one going at the bottom, which is a red ball, all right? And then again, coming towards me, all right, coming towards me is a yellow ball. Going away from me is a white ball, okay? So this is what you should be expecting, or this is what you should be getting on the paper on your exam. And if you're able to go from here to this structure, or you're able to visualize that what actually that representation means, it means nothing but this carbon, right, having a green ball facing towards me, meaning facing right, coming towards me away from the plane of the paper, and then the orange one going away from me or in the plane of the paper. And then at the back one, again, the yellow one is coming towards me. You can see that here it's coming towards me, right? And the white one, again, is going away from me. And the red one is at the bottom, correct? So that's one thing that you have to be able to visualize. This structure, wedge meaning coming towards me, dash meaning going away from me. Again, wedge meaning coming towards me, dash meaning going away from me in both of these carbons, okay? And once you're able to visualize and once you're able to be here, right, in your head. So this is going to be in your head because you don't have a software to play around with, or you can actually use the software to play around with. I'm using Avogadro at the moment, okay? And now what you're supposed to do is to convert this into a Newman projection, you have to put yourself at C1. You have to be able to be here at C1. Now, once you're here at C1, right, the next thing to do, or the next thing to know once you're at C1 or viewing C1, so you are over here and looking at C1, what you see on your left is the orange ball, okay? So what we do essentially is we go back to the drawing board, all right? And we have this carbon, right? This is the carbon. And on my left, what I see, and this is also C1, so I'm gonna call that C1. And on my left, I see, so because I'm right over here, on my left, I see the orange ball. On my right, I see a green ball, right? And on top, facing up top is a pink ball, right? So this is nothing but a representation. We are starting to represent that structure as a Newman projection. Okay, and now what about the back carbon, right? So we have, the problem is going to tell you that you have to view the carbons facing the C1. So it will tell you that the eye of the viewer is at C1, meaning you're standing over here, meaning you are at C1, meaning the front carbon is the C1 carbon, okay? Then which will automatically make the C2 carbon as the back carbon. And now once the C2 carbon is the back carbon, what we're supposed to do again, so to represent now the back carbon, we draw a circle. So the front carbon we represented as a dot, right? And all the spokes of that red carbons, or all the spokes of that front carbon would be the substituent of the front carbon. And now the back carbon is nothing. So the back carbon is just juxtaposed on the front one. What does that mean? So in the Newman projection, we're supposed to kind of align the front and the back one such that we don't actually see the back one. So once we don't see the back carbon, right, what we have on the left is what I see on my left is the white ball, right? What I see on my right is the yellow ball. What I see at the bottom is my red ball. So now the spokes coming out of the circle of that Newman projection are the substituents of the back carbon. And now we don't really represent the back carbon because it's supposed to be hidden because it's overlapping the front carbon, right? And this is nothing but a Newman projection. So let's think about this, right? What I essentially did is, this was the molecule given to me on the plane of paper in the problem. And the problem is really making me juxtapose C1 and C2, the front and the back one, right? And don't forget, it's going to be different if you have the C2 carbon as the front carbon. The representation is going to look different, right? Now you're going to have this representation. But let's go back to C1 really quick again. Now you're at C1, okay? And so it just wants you to understand, basically, do you understand the 3D geometry of the molecule? Do you understand how this molecule looks like in space? If you do, can you please move it around for me such that now I have C1 and C2 on top of each other? That's nothing but a Newman projection. And that is so simple if you look at the model. If you look at the model of your compound, right, just moving it around, this is my Newman projection. But it's hard because you have to kind of visualize this structure, right, in your head as a 3D structure, which would look like that. And then you stand over here and visualize where left, right, where all your substituents are lying on that plane. And then you go ahead and draw out that Newman projection. So this is now your Newman projection. Okay, and now let's talk about why should we even think about Newman projection, right? Why is it helping us? Why have chemists made such a big deal about Newman projections? Okay, so the reason for that is that, do you see how easy right now it is to see the angle between the front carbon and the back carbon, right? Between pink and yellow, you can see the angle is 60 degrees, right? And if I have this molecule represented just like how it is right over here, I can't really tell the difference between pink and yellow, can I? It's just kind of a little difficult to kind of tell the angle, right? And these angles between the front carbon and the back carbon, actually the substituents of the front carbon and the back carbon, these angles are named as dihedral angles, especially because they're on different carbons, right? On the substituents of different carbons. So because it gets easier to know the angles between substituents of different carbons, the first one, the second one, the front one, the back one. That's why, first off, it helps us to know the angles. That's why they're very popular. Newman projections are very popular, right? And then the next extrapolation, the obvious extrapolation is, why is it important to know the angles between the front one and the back one? Because the angles decide the stability of the molecule, right? If the substituents of the front carbon and the back carbon are really close to each other, then they provide some kind of steric hindrance, right? And other kinds of hindrances as well. So they can provide steric hindrance. So because of their large size, they will their electron clouds are not going to be happy. They would want to repel each other. And that's why the lower the angle, right? Or, if they're really close to each other, there will be more repulsion, and the more unhappy the molecule is going to be. So if these angles are really far apart, right? So if I had a Newman projection where I had pink over here, orange over here, and green over here, and for the back one, right, if I had the biggest one, let's say if that was the yellow, if the yellow was over here and the red was over here, and then the white was over here, right? In that case, is that right? Have I drawn it correctly? Yellow's over here. Yeah. So now the dihedral angle between pink and yellow is 180 degrees, right? Now this is 180-degree angle, and this is good. This is, we want the maximum angle. Now they're so away from each other, their electron clouds are not going to repel each other. But again, you should think about there's still this dihedral angle. There's a 60 degrees dihedral angle over here, and then there's a 60 degrees dihedral angle over here. So now whenever we have situations like these, we think about the size, right? And that topic we will cover in the next video, which will talk about how sizes decide or help us decide the stability of these molecules. And then we'll also include the dihedral angles, including the Newman projections. All right, I hope this video helped you, and have a great rest of your day. If you have any questions, please let me know. I'll be happy to answer any questions you have.